Hello, all part of this video lecture, looking at some slightly different topologies for the circuits. This time I'm going to use this circuit with the capacitor and the inductor in parallel and the resistor in series with that parallel combination. And I'm looking at my output voltage across the parallel combination of the capacitor and inductor. Going through the standard potential divider method for deriving the frequency response ends up with this. Now, compare that to the previous circuits that we've been analysing, which have a series RLC, and I'm taking the output across the resistor. And the answer is, well, if you compare them, you'll note that the resonant frequency in both cases is exactly the same. 1 over the square root of LC. It's the frequency at which the impedance of the capacitor exactly cancels out the impedance of the inductor. The Q factor, however, has inverted itself. This Q factor is 1 over this Q factor. So we've inverted the Q factor by moving the components around in the circuit without affecting the resonant frequency at all. What about this one? Well, if you compare that one to this expression here, to the expression that we got here, you'll notice they are exactly the same. So this circuit, with the output taken across the capacitor and the inductor in parallel, has exactly the same frequency response as this circuit, in which the inductor is in parallel with the resistor and the output is taken across the capacitor. Finally, a slightly different one. This one has two zeros in its response because we have a quadratic expression on the numerator here. So we've got two zeros, but neither of those zeros is at 0 Hertz. We have a couple of poles as well. It's interesting, however, to note where these zeros are. You can consider zeros to have a resonant frequency and a Q factor as well. But in this case, the Q factor associated with our zeros is infinite. That means that the two zeros are both imaginary, and they are at complex conjugate frequencies, but totally imaginary frequencies. We can show that perhaps by looking at this numerator and comparing it to the general form of two zeros. That would be 1 plus j omega over z1 plus 1 plus j omega over z2. That's what we'd expect on the numerator if there were two zeros, neither of which was at 0 Hertz. What values of z1 and z2 do we need to make this equal to this? Well, multiply this out. 1 plus j omega, 1 over z1 plus 1 over z2 plus j omega squared over z1, z2. Clearly, z1 times z2 is going to be 1 over LC, and that's the square of the resonant frequency in this case. But 1 over z plus 1 over z2 must equal 0. Which means that z1 plus z2 must equal 0. The sum of the two zeros is always 0. Given the fact that zeros always occur either as real numbers or in complex conjugate pairs, the only way this can happen is if z1 is j omega naught and z2 is minus j omega naught. Then z1 plus z2 would be equal to 0 as required, and z1 times z2 would be equal to omega naught squared as required. We have two zeros, but they are perfectly imaginary zeros. What that does in practice is it produces a notch filter. And a notch filter has a very, very sharp dip in its response. We can simulate it. The simulation of a notch filter looks like this. You can simulate any of these circuits, and it's quite good practice. This is a simulation of my notch filter with a 1K resistor, a 1 nanofarad and a 1 millihenry, and you'll see that the gain of this circuit is pretty constant and pretty close to 0 dBs until you get close to this frequency where the zeros start to take effect, and then you get a very, very sharp dip coming back up again. So there's a very narrow range of frequencies for which this filter removes any energy, any signal around. Around these frequencies there's attenuation. At high frequencies everything's let through, at low frequency everything is let through, just not around the notch. And it's a useful circuit to build if there's one particular irritating frequency that you're trying to get rid of in your circuit. Right, that is all I wanted to say in the lectures this week. Frequency responses and poles and zeros Quizzack topics are live. Please get moving. And next week we're going to be talking about second order step responses, what the step response is of these circuits with RLC networks, resistors, capacitors and inductors. Thanks for watching.